To start our video on electricity, I will define three distinct quantities: potential difference, current, and resistance. Potential difference, or voltage, is denoted by V. It is equivalent to the work done in moving a charge from point A to another point B divided by the magnitude of the charge itself. This quotient, then, is the potential difference between points A and B, given using the SI unit volt. The electric current running through a wire is defined as the rate of flow of charge through the cross-sectional area of the conductor. The unit for this is the fundamental SI unit ampere, or 1 coulomb per second. Resistance R is the quotient of potential difference and current. This unit, the volt per ampere, is denoted using the Greek letter omega and is known as an ohm. This formula is also commonly known as Ohm's law, named after the German physicist George Ohm. More specifically, what Ohm discovered was that provided the temperature was kept constant, the current of a conductor would be proportional to the potential difference across it. Materials that obey this relationship are known as ohmic conductors. Additionally, for resistance, it has been proved experimentally to be proportional to the length L, but inversely proportional to the cross-sectional area A of a conductor. This was used to define the relationship that R equals rho L over A, where the Greek letter rho denotes the resistivity of the wire, which depends on the material and temperature. Its unit is the ohm meter. We can now apply this to some practice problems. Consider, for instance, a wire with a current 2 amperes with a voltage 10 volts and a current 4 amps with a voltage 20 volts. Try calculating the resistance in both cases and checking if this is an ohmic conductor. This is a simple application of Ohm's law. At first, we have R equals 10 over 2 equals 5 ohms. Secondly, we have R equals 20 divided by 4 equals 5 ohms. Since the resistance is constant, it must follow that V and I have a linear relationship, as is easily confirmed by looking at a graph. Increasing the current by a factor of 2 does the same for the voltage. Hence, they are directly proportional, and this is an ohmic conductor. Let's consider another scenario in which we have two wires X and Y, which are made of the same material and have the same length. Wire X has a radius r and wire Y has a radius 3r. We need to determine the ratio of the resistance of wire X to the resistance of wire Y. To do this, we first consider Rx. This is equivalent to rho L over pi r squared. Ry then is given by rho L over pi 9r squared, as we need to remember to square the factor of 3 as well. If we divide the two expressions, we see that all constants cancel out, and we are left with Rx on Ry equals 9 over 1. Hence, Rx equals 9 Ry. To further this explanation, we can consider the electric power. We saw previously that voltage is the quotient of work and charge. By rearranging algebraically, we find that the work done in moving a charge Q from points A to B is given by QV. Hence, the power, which is defined as work done divided by time, will be given by QV over T. But Q on T is the definition of current, leaving us with the result that power is the product of current and voltage. We can then use Ohm's law to write this in the equivalent forms Ri squared and V squared over R. Now, we can do one final worked example. Consider a custom heating element made of nichrome, which has resistivity 1 × 10⁻⁶ ohm meters. It is cylindrical with length 0.5 meters. Additionally, when connected to a 120 volt source, it must dissipate exactly 1.5 kilowatts of power. We need to determine the required radius of the cylinder. To do this, we first find the resistance, which can be done simply through substituting our values into the formula P equals V squared over R, giving R equals 120 squared over 1500, which gives 9.6 ohms. Now, using our formula for resistance, we find that A equals rho L over R. Substituting our values, we find that A is approximately 5.21 × 10⁻⁸. In this case, we are using a cylinder, so the area is pi r squared. Thus, R equals the square root of A over pi. This resolves to approximately 1.3 × 10⁻⁴ meters, or 0.13 millimeters. Thank you for watching, and have a good day.